To test for concavity, let f be a function whose second derivative exists on an open interval I. If f double prime of x is greater than 0, in other words, the second derivative, for all x in I, then the graph of f is concave upward on I. If the second derivative, f double prime of x, is less than 0 for all x in I, then the graph of f is concave downward on I. Looking at the example, determinant of the open intervals on which the graph of f of x equals 6 over x squared plus 3 is concave upward or concave downward. It is important for us to first note that f is continuous along the real number line. In other words, there are no domain restrictions along the x-axis. Then, we'll want to find the second derivative for f. To find the second derivative, we can rewrite this as 6 times x squared plus 3 to the negative 1. Applying the product rule, we consider our factors 6 and x squared plus 3 to the negative 1. Times the derivative of x squared plus 3 to the negative 1, which is negative 1, times x squared plus 3 to the negative 1 minus 1, which is negative 2, then times 2x, applying the chain rule. Multiplying these terms together, we get negative 12x divided by x squared plus 3 to the power of 2. Now we need to take our second derivative, f double prime of x, and here we may find it more helpful to use the quotient rule. That gives us x squared plus 3 squared times negative 12 minus negative 12x times 2 times x squared plus 3 to the first times 2x. And I'm going to rewrite this so it looks a little bit neater. And rewrite this all over our denominator squared. So we have x squared plus 3 squared and we are able to simplify this to 36 x squared minus 1 all divided by x squared plus 3 cubed. Setting this statement equal to 0 and solving for x, multiplying x squared plus 3 cubed on both sides, this would cancel. And so we'd have 36 times x squared minus 1 equals 0. Dividing 36. This cancels. X squared minus 1 equals 0. would become x equals 1 and x equals negative 1. Now we know that f prime of x, or f double prime of x, is equal to 0 when x is equal to plus or minus 1. So we test f along the real number line from the intervals negative infinity to negative 1, negative 1 to 1, and 1 to infinity. We can choose our test points arbitrarily. I need a test point to the left of negative 1, so I'll choose negative 2. A test point between negative and positive 1 could be 0. And a test point between 1 and infinity, we could use positive 2. If we evaluate f double prime at negative 2, in other words, plugging in negative 2 for all x in the second derivative, then we'll get a positive number result. F double prime of negative 2 is greater than 0. If we evaluate f double prime at 0, by plugging in 0 for all x in the second derivative, we find that f double prime of 0 is less than 0. And finally, f double prime of 2 would turn out to be greater than 0. And again, all we do here is plug in our value. For example, f double prime of 0 would be substituted for all x in our second derivative. So in the numerator, we'd have 36 times negative 1. In the denominator, we'd have 3 cubed. Negative in the numerator, positive in the denominator means that our result would be negative or less than 0. Based on these results, we're now all able to determine the concavity when f double prime of negative 2 is greater than 0. I know that this is concave upward. F double prime of 0 being less than 0, that's concave down. And finally, f double prime of 2 is concave up. This concludes our example, and we'll see you next time.